Okay, this is Andrew. We're going to look at the solution for the subnetting quiz. Um, First, we're going to talk a little bit of history just to understand why we're subnetting. So initially, in the old days, they had like RIP version 1, which was a routing protocol, and you would have a class A, B, or C network, this being a class C, the 192.168.1.0, and it had no subnet mask, right? It's just the 192.168.1.0 was the network, and you had from 0 to 255 in this quadrant, where 0 was the network address and 255 was the broadcast address, and then the 1 to 254 in this space could be used to assign IP addresses to devices. Well, that was great and it worked, but if you only had 5 computers, then out of that 254, you had you know 249 wasted spaces or whatever. So you can see that wasted all that space, and the problem with that is if you do this 2 to the 32 for the number of bits, it comes out to like 4 billion, which just isn't enough IP addresses for all the devices on the planet. So they started coming up with these hacks to extend the IPv4 addressing space, and NAT was one of the hacks, private addressing was one of the hacks, and subnetting was one of the hacks. So they added this part, the subnet. So now the class A originally had the first 8 bits were 255 and the rest 0. Class B, were the first 16 bits, were 255, 255, and 00. And class C was like this: 8 bits 1, 8 bits 1. So the first 24 bits were 1, and the last were 0. So you could only assign hosts in this space. Well, what they allowed you to do, the addition of this subnet mask does, it allows you to assign in this space. So you now have a class C network address, but in this space of 8 bits, you can assign anything over to the left as network of bits, and anything to the right is host bits. So I can, out of these 8 bits, I can take 2 to the left, which would be 128 plus 64, which is at 192. I could take 2 to the left and assign them to networks, and then the 6 bits to the right would be host bits. So then I've reduced this network. I've broken this network into subnets. So that's what subnetting is. Okay, so first thing we're going to do is write this network in CIDR notation. So the network is 192.168.1.0. This is 8 bits all 1, 8 bits all 1, 8 bits all 1. So that's 24 network bits slash 24. That's really what this 24 means, is how many network bits. So if in this space, in this 256 space, if I take the first 2 bits and turn them to 1 and leave the other 6 0, then I've borrowed 2 bits out of this space to assign to network bits. So in that case, I would have 24 plus 2. It would be a slash 26. All right. So this thing is saying how many, if I'm doing 4 equal subnets, right, of 50 PCs, well, it's telling me 4 equal subnets, so I have to do 4 equal subnets. So what's 256 divided by 4? 64. That's the block size. So do 50 PCs fit in the space of 64? Yes. So basically we took this space of 256 and divided it into 4 spaces, 64. So this is really, it's given us 4 different subnets. And what does that actually mean? What it really means is, how like on a router we said each branch is its own network. Well, so let's look at the actual project quickly. So what did this do for us? We had one network that was 256. So now we divided it into 4 equal subnets, and that's giving us a block size of 64 minus the broadcast and host address. So we have 62 IP addresses that we can use to assign to devices on that network. So what does that mean? If you look at this router here, for example, we have 1, 2, 3 networks, right? Well, if I use this 192.168.1.0, I would have to use that one for this network. So then I could assign 4 IP addresses, 1, 2, 3, 4, for these servers, and the rest of them are wasted. I can't use the 192.168.1/24 up here. But since I subnetted it, I now have 4 equal subnets of the 192.168.1.0. So I can use one here, one here, one here, and I even have another one left over for another branch. But the difference is now this was a /192.168.1.0/24, but now it's a different subnet mask. It's not a .0 anymore. It's a subnet mask. So what we're doing really is we originally had the 192.168.1.0 and they did not have a subnet mask, but now we're adding this subnet mask and we're telling it how many of these bits do you take out of this space to add to the network bits down here at the CIDR notation. And by doing that, you've literally broken this network into different subnets such that you can assign IP addresses on different branches of the router. And what that means is you can use nearly all the IP addresses in this space without wasting large amounts of IP addresses. Of course, you need to save room for planned growth. But don't forget too, like in this example, there would be another interface on the router. So, if we grew too many, company just grew so large that we had to add more PCs, then we can just add another network here as well. We don't necessarily have to add everything to this subnet. Okay, so I hope that makes some sense and at least clears up the concept of what we're doing. So anyway, you're given this subnet and you want to divide it into 4 equal subnets. So we see here it's 8 bits. That's a space of 256 divided by 4 gives you 64, minus the 2 for the network and broadcast address gives you 62. So what actually are the subnets? Okay, well, it's simple. You just start at 0 and you add 64. So 192.1.0 plus 64 goes up to 192.1.63. Okay, great. So now what do? You just add 64 more. So it's 64 to 127. And then you add 64 more. So it's 128 to 191. And then you add 64 more, which is 192 to 255. So what's the IP address range of each subnet? That's just the values between here. That's what you can use. So it's 1 to 62, 65 to 126, 129 to 190, 193 to 254. Okay, so let's write this in CIDR notation, okay? So you can see these are the subnets, but it doesn't have a mask. So let's write it in CIDR notation. So 192.168, sorry about that, 192.168.1.0, how do you get the /26? Okay. Okay, so let's go back up here and look at this. So you remember these are 8 bits each one of these quadrants. And the ones to the left represent the network bits, and the zeros to the right represent the host bits. So this is, at this time, this is 8 bits you can use here. This is telling you this quadrant like maps to this one, and it's telling you, and this quadrant maps to this one, and this quadrant maps to this one, and this quadrant maps to this one. And this is telling you that all of these bits are ones. This is telling, the second quadrant here is telling you all these bits are ones. The third bit's telling you, the third quadrant's telling you all these bits are ones, and the fourth quadrant is telling you all these bits are ones. And if we write that inside our notation, that's a /24. But now, what you're wanting to do is you want to actually borrow some of this, some of these bits from this space and make them network bits. So out of these 8 bits, if you need 64, how many do you have to take? Well, there's 2 ways you can do it. Okay, is 2 to the 6 is 64. So 6 bits would be host bits, and that would leave 2 for network bits. So you'd have 1, 1, and then 6 zeros. So 24 plus 2 would be a /26, right? So we can see down here we have a /26. So that's one way of looking at. Another way is you could say, okay, well, if all of these, this is the way I just like to do it because it makes sense to me. If all these bits are all ones, then it's a total space of 256, right? So if I subtract 64, which is the block space that we need for the hosts, then we're left for 192. We're left with 192. And 192 is the first 2 bits. So you can see 192 is the first 2 bits. So actually 192 is going to be the subnet mask. If you convert the 26 CIDR notation into subnet mask, which is what we want to do, subnet mask equals the first 2 bits in the quadrant. So it's 128 is the first bit plus 64 equals 192. So you can do it either way. You can say, okay, in this space I need 64, and 2 to the 6 is 64, so I need 6 host bits. Or you can say the total space is 256, and I need 64, a block size of 64, so I need 192, and then 192 is 128 plus 64, which is 192, which gives you 2 bits. And it's actually easier than that sounds because there's only a certain amount of combinations. There's there's just 128, 64, 32, 16, 8, and 4. So, I think we went through a video of that. You only have to remember, eventually you don't even have to work through these. You just memorize the cases, and I did a video of that. So you can, either one. All right, so now remember, again, this is still an introduction class, and this is an introduction to networking and subnetting. There are longhand methods where you actually manipulate each bit according to procedures, and it gives you the correct answer, because the problems do get more complex. As say you're doing a class subnet in a class B, and you want to break this into 3 more networks bits here, such that you have 11 network bits and then all these host bits. Well, what happens in a case like that is you can still do it all in your head like this, but it could be more complicated. It can get more complicated is what I'm saying, although the concepts are the same no matter how you subdivide this, and you can eventually do any subnetting in your head if you just get practice with it. Of course, like anything else, if you don't practice it often, you might need to review it. All right, so is this a VLSM or just subnet masking? Why? Okay, so what's the difference between variable length subnet masking and subnet masking? Subnet masking is, well, let's look at variable length subnet masking. That means if we broke this into 4 different subnets, the length of the subnet would vary, meaning that one might be a 25, one might be a 26, one might be a 27, one might be a 28. All these are the same, so this is just subnet masking. This is not variable length, okay? So variable length is subnet masking is you have to take the block sizes like the 128, 64, 32, and choose the block size you need to fit for the amount of clients or devices that are going to be put on that particular subnet. So again, in this example, if I had one subnet, if I had two more subnets, but I knew each one was only going to use let's say I had four more subnets, but I knew each one of them were going to use less computers, then I wouldn't have to break this into equal spaces. Like if well, let's just say let's say some of these are using less, then I don't need a 64 block size. Like say if it's only 20 computers, then I only need a 32 block size. Or if it's only 12 computers, I only need a 16 block size. So you would break the space into smaller pieces, but still allow enough room to growth. And as technology changes, sometimes these networks that were designed originally become a problem, because in the old days they didn't leave as much space as you would now, especially for bring your own devices and things like that, because they have to have IP addresses too. But these days you see, everyone brings their phone or tablet and they want to access the network. So if those spaces aren't available, then you have to go in and do a lot of rearranging on the networks, which can cause routing problems and all kinds of headaches. All right, so thanks a lot. I hope this helps clear up some, not only how to subnet, but why we subnet. And be aware that the IPv6 addressing is really the final solution to the address space problem. Although everybody that has IPv4 addresses still use them. So, but another problem is companies, or as they expand, there aren't really any IPv4 addresses left, so they have to use IPv6 addresses. So your company starts mixing IPv4 and IPv6 addressing, and it starts becoming a nightmare. All right, thanks.